Let's go.
Yeah, okay, so first of all, I have a low charge on my headphones. Maybe sometime after the lecture, I'll have to turn them off. I hope this won't interrupt us. Yeah, so today I'd like to talk about Ethereum transactions in blocks and how are they built, how do they work, and etc. etc. So let's start with transactions. So first of all, what is a transaction? Transaction is an atomic action initiated by an externally owned account that either changes the Ethereum state or reverse. So what does it mean? It means that there is a Ethereum from the previous lecture. We remember that Ethereum is usually called a world computer. So there is a world state, let's call it T. The user sends a transaction, it executes, and the state changes to T+1. Only externally owned accounts can send the transactions, so smart contracts that are deployed on chain can only react to those transactions. And yeah, that's it. So there are three main types of transactions on Ethereum. First one is the regular transaction. It is the one when user wants to send Ethereum or Ether from his account to another account. It is the simplest, like the most simple transaction possible on Ethereum, and it is the cheapest one. The second type is the contract deployment transaction, where to field is set to like a special value, and the data field of the transaction is set to a contract creation bytecode. So we'll talk about this like later in the lecture and in the upcoming lecture when we'll touch the smart contracts and solidity. But basically it is here like for the example. And the third type, it is actually the most common one, is the transaction that interacts with smart contract. And to send this type of transaction, the to field has to be set to a smart contract address, and data has to be like specially encoded in order for the smart contract to understand it. And that is how the smart contract will like react to whatever you want to do with it. Okay, so what is inside a transaction? There are quite a lot of fields that are propagated by the wallet. Some of them are automatically added. Some of them actually the user themselves specifies. So what do we have here? The nonce field. The nonce field, it is the like special field that is present in every transaction, and it is used to uniquely identify the specific transaction with the other parameters. So because like anyone can send any transactions on Ethereum, it is possible for the same user to send two identical transactions. So with the same fields, but the nonce field will always be unique. And it is achieved by Ethereum by basically counting how many successful transactions as an externally owned account sent. So if you interacted with a smart contract, or if you sent Ethereum somewhere, or if you deployed a smart contract, then nonce value would increment, and Ethereum like Actually, Ethereum doesn't store it anywhere. And when you send transaction via your wallet, the wallet asks how many transactions are successful, and then adds like 1 to this number. It becomes like the nonce of the next transaction. But it is a requires field. Yeah, then there are 2 fields that are added after the London hard fork. London hard fork was made, I think, like a year and a half ago, somewhere in maybe July 2022 or 2021. And it proposed to change the like common gas that is, for example, using Bitcoin to a more complex one. And what we have right now is 2 variables. The first variable is the variable that actually is the same as in the previous consensus, and it acts as a fee that you pay directly to the validator that will like mine your transaction, that will include the transaction in the block. And this variable is added into the transaction, and it is called max priority fee per gas. It is the tip that you will pay to the validator, like an extra tip. You can like specify it to whatever you want. And then there is a second variable that is based on 2 another variables. So first one, priority fee. It is this priority fee, max priority fee per gas, and the base fee. And the base fee is the fee that Ethereum sets automatically by himself for each block. And if your transaction has base fee lower, then you want to, if you send the transaction with the base fee that is lower than in the current block, then Ethereum won't accept this transaction. So for a successful one, you have to specify this value to be bigger or equal to the base value of the block. And then the priority fee is included on top. And the sum of these 2 variables is the max fee per gas. So pretty complex right now, but actually this setup is like much more agile than it was before. This setup allows for the dynamic, like right now Ethereum can react to spikes in congestion. So when the load is high, Ethereum can increase the base fee of the block, and because users have to pay more for the transactions, the load should decrease. Okay. Then we have a gas limit. The gas limit is a parameter that is set to every transaction, and it indicates how much gas can transaction consume when it is executed. And this value can be set to a pretty much arbitrary number. It has to be more than 21,000, because 21,000 is just a standard that no transaction can be cheaper than 21,000 gas. Actually, sending Ethereum from one account to another, which is the cheapest transaction, costs only 21,000 gas. So you can specify pretty much any value, and when you, for example, execute a smart contract, if it happens a transaction consumes more gas than the specified gas limit, then it's basically a reverse. So no changes are going to be applied. Then there is a field called recipient. It is the destination Ethereum address, and it is the one that will react to your transaction. It can be an externally owned account if you want to send Ethereum, or it can be a smart contract if you want to execute some code, or it can be a special address 0 to deploy a smart contract. And then there is value field. Value field is set when you want to send Ether to a recipient, the one you specified in the transaction. If this value is 0, then no Ethereum is sent. And in that case, you will probably specify some data to interact with smart contract. Because usually smart contracts work with their own tokens, their own NFTs, and it is not the native Ethereum that Ethereum is built on. So usually when you interact with smart contracts, this value will be equal to zero. And data field, it is a special field that is encoded, like ABI encoded. And it basically states which function with which parameters the transaction is going to call on the smart contract that you specified as a recipient. So using this data basically allows you to interact with smart contracts. Interact with smart contracts. So these are the main parameters of the transaction. But in order for Ethereum to actually include the transaction into the block, you have to sign the transaction with your own keys. So every externally owned account has a private key and a public key, which they generate on their own off-chain. And once the transaction is specified, it is encoded in a RLP, via RLP algorithm, and then signed with the private key of the externally owned account that wants to send this transaction. And the CDSA signature comes with 3 parameters. And those 3 parameters are sent to the network. Okay. So, so there are several transaction parts that I want to point out. That transactions are actually not as simple as they are in Bitcoin. They're a lot more complex and complicated because Ethereum is rapidly evolving blockchain. A lot of new standards are proposed, a lot of new improvement proposals are implemented, and they always want to add something new. So that is why, for example, in the EAP at 718, this EAP introduced a special transaction envelope that to allow future transaction implementations. What I mean by that is, for example, before the London hard fork of the Ethereum, the fee per transaction was different. It was just one variable, the same as in Bitcoin. That if you want your transaction to be fast, this variable has to be high. If you are okay that your transaction is going to mine like several minutes, then you can set it to a lower value. But after the London hard fork, this changed. So Ethereum had to adapt to understand those changes. And basically this improvement proposal described how to implement those changes in the Ethereum node to support different transaction types. Due to this proposal, right now we have, I believe, 3 different transaction types. First one is the legacy one that was used before the London upgrade. Then there is one that was introduced like long ago to mitigate replay attack protection mechanism, and then there is a new one after the London hard fork with those strange fees. And right now, Node understands all of them due to this proposal. So what I have already said, when Ethereum was launched back in 2015, the chain ID wasn't included in the transactions, so it was possible to replay several transactions on different chains. So because back in 2015, Ethereum was the only EVM chain, it wasn't a problem. But right now, there are many blockchains that support EVM, for example, Binance Smart Chain or Polygon, and they have similar transaction structure and accounting system. And in order to distinguish transactions on, for example, Polygon and Ethereum, there has to be some parameter inside to indicate to which blockchain this transaction belongs. And the chain ID is a special parameter that is added to those like transactions. For Ethereum mainnet, it is 1. And I believe for Binance Smart Chain, it is 40. But yeah, you have to verify that. And yeah, it is expected that chain ID is unique for every serial virtual machine blockchain. Oops. Then the transaction hash is calculated as a Keccak 256 hash of the signed RLP encoded counterpart. What I want to say here is that the hash of the transaction is absolutely deterministic, and it is based on the content of this transaction with the signature. So it is not this data, but data together with the signature that is RLP encoded on top. And yeah, because when we have unique nonce for pretty much every transaction, that means that it is impossible to have transactions with the same hash. Then, if you were attentive enough, you would notice that in this table, the from parameter is missing. So why is it like that? Because from parameter can be actually deduced from the signature itself. Because ECDSA signatures support recovery. That means that from the signature, you can identify who actually signed the data by providing the signature and the data they signed. And if everything is fine, you'll receive the account that made the signature. So basically, nodes do exactly that. And for example, in block explorers, you will find if you search for a transaction and go inside this transaction, you will find the from field. But this from field is actually deduced from the signature by providing all data and recovering the address. Okay. Then let's wrap up the transaction lifecycle. So what happens the first? Transaction is constructed by the user. Wallets may help with the construction, for example, by calculating the required gas limit for this transaction to succeed, or by calculating the required cost price and automatically setting it for the convenience. Then the transaction is signed with the private key that is held in the wallet and RLP encoded for the future broadcast. Then transaction hash is calculated, and in this way, the transaction is broadcast to the network, to the node, and added to a so-called mempool. Mempool is the special memory, memory pool in the Ethereum nodes that store pending transactions. Then validator picks a transaction from this mempool and includes it in a block. And finally, the block gets added to the chain and the transaction executes. So it is important to understand that transaction only executes when it is added to the block, and the block is included into the blockchain. So there are several cases when the reorganization of blockchain might happen, even on Ethereum. So it is really important to wait several blocks, or even maybe not several, but like 20 or 30 blocks in Ethereum to check the finality. Okay. So yeah, then let's talk about the blocks and how are they constructed in Ethereum and what is inside those blocks, how Ethereum works for them. So blocks are batches of transactions that actually are mainly needed for the optimization purposes. It is completely fine for the blocks to contain one transaction. And it is common to see in some test environments, for example, when you're writing your smart contracts and running your local blockchain for the fast interaction. Usually those blockchains will mine blocks when they receive a single transaction. But because Ethereum is a public blockchain, it has a lot of validators and a lot of users, those transactions have to be aggregated into the blocks just to increase the throughput of the blockchain to make it feel a bit faster. And from this diagram, we see that actually the state changes when the block is accepted. In the previous diagram, there were no blocks, which is not exactly true. So this is like more real-world diagram, more correct one. So what is inside a block? Right now, block is a really complex structure that contains both the intricate proof-of-stake consensus information and the information about transactions. Before Ethereum switched to proof-of-stake, only the transactions execution payload was present in the blocks, but right now the structure has like grown maybe 3 or 4 times. I will show you in the next slide. Blocks in Ethereum are really, really complex. When Ethereum switched to proof of stake, they basically added this execution payload into the proof of stake block, and it became just one of the parts that right now Ethereum operates with. And in this execution payload, there is a list of transactions that validators pick and execute one by one when the block gets added to the blockchain. So let's have a look at what was before the proof of stake and what is right now happening with the blocks. So we have 2 huge diagrams here. On the left, it is the after proof of stake thing, with this tiny block being the diagram on the right. So all of this is added here, and then on top, it is the consensus things that Ethereum does. Before proof of stake, only diagram on the right was present. And in this lecture, I won't cover the consensus thing in depth. I will only talk about the thing on the right. Because, yeah, it is quite complex, and only talking about the consensus parts would take us probably a lecture or 2. Okay, so what do we have here on the right? The block actually consists of 2 parts. It is the block header and the transactions that this block has. There are a lot of parameters and that the block has, and let's talk about them in depth. The execution layer structure. What do we have here? We have a parent hash. As Ethereum is blockchain, blocks have to be linked between each other, and then every future block has a reference of the previous block, and this reference is included into the current block. So pretty obvious. And there is a hash of the current block, which is actually the hash of everything that that is in the block, and this hash represents the state of the Ethereum, the whole state. Ethereum state is much more complex than in Bitcoin, because first of all, we have to know the Ethereum balances of individual accounts and smart contracts. We have to know the state of every smart contract, because it can do whatever the smart contract wants, obeying the rules of Ethereum virtual machine. but still each transaction can modify the state of each smart contract. So we have to account for that. Then there is a special thing called receipts. This is a data structure that is maintained by Ethereum, and it is the information about the transaction receipts. So it is how many gas it consumed. I don't know, maybe like several other fields, but it is information that is only available after the transaction gets executed. Then there are logs. It is a special feature of Ethereum that every smart contract can emit special events that, I don't know, for example, there is a USDC token, and when one user sends USDC token to another user, there is an event emitted that user A sends 10 USDC to user B. And those events are also stored on chain. And the block has to collect all this data, so users are certain that nothing changes in Ethereum. So those fields and those data structures, so everything here is stored in a special data structure called Miracle Patricia tree. I won't cover this data structure right now, but it is a special thing that allows blocks to quickly verify the state, and it is like quite easy to implement. So everything about those data structures, their state, is included into every block, or every block that is mined. Then there is a fee recipient. It is the address who is going to receive some of the transaction fees. Why some of the transaction fees? Because if you remember, there are two types of fees that users can pay. The first one is the base fee of the block. This fee gets burned. And the second one, the tip, gets paid to the fee recipient. So just for transaction priority. And also fee recipient receives the rewards for network participation from proof of stake consensus. Then there is a field previous rundown. What is it? It is a pseudo-random proof of stake number that is used in the proof of stake consensus to determine who will be the next validator to vote or to decide which transactions to include into the block. And each block so from it is like the current rundown, but it is named previous rundown because if you want to get this variable from the smart contract, this variable will be known beforehand. So it is not the random that you will get like instantly. It is already known random, and not to confuse and not to force developers to understand that it is not a pure random, it is named as previous random, which is like kind of correct. Yes, and this variable actually substituted the mix hash variable that was present when Ethereum was proof of work blockchain. So right now this mix hash is obsolete, and pre-Brandao substituted it. Then difficulty is a legacy feature that we received from the proof of work Ethereum, and before it was used to to adjust the Ethereum difficulty when, for example, blocks were mined too quickly or too slowly. Right now, this difficulty is not used, and it is left as a legacy field, not to break the block structure when it is represented in bytes. So they decided to leave it like always to 0 and let it be there. Then there are two variables, the gas limit and the gas used. Gas limit is the maximum allowed gas that the transactions that are included in this block can use. Ethereum has a variable gas limit, which is adjusted when the load gets high or low. Right now, the gas limit is equal to 15 million. And when the gas limit, the actual gas limit of the block exceeds the 15 million, then the base fee per gas gets increased, which makes users pay more. So that reduces the congestion. The maximum gas limit that the block can grow is up to 30 million. And beyond that, every transaction that consumes more than 30 million gas will basically revert or not included at all. If you specify the gas limit more than the block gas limit, then the node will just reject your transaction. The base fee per gas variable, it is one to control the congestion of the Ethereum. If the load is low, then the base fee per gas will decrease to make the transactions cheaper. So to maintain the gas limit to stay always in this 15 million zone. And this variable is maintained by the Ethereum itself. Timestamp, when the block gets included, it is added the timestamp, the Unix one. And right now, blocks are mined every 12 seconds, which is set by the rules of proof of stake. Before proof of stake, it was 13 point seconds per block on average, but right now it is strictly 12 seconds. Which actually allows for flexibility on smart contracts, because you can predict the block number, like, I don't know, which block number will be in a year. Okay, so let's wrap up the block thing with its life cycle. So number one, the block validator is pseudo-randomly but deterministically chosen via proof of stake consensus algorithm. So that means that contrary to Bitcoin, where every miner like solves the puzzle to become the one who is going to receive the rewards. In Ethereum, the validators are chosen by the proof of stake algorithm, like pseudo-randomly, but deterministically. You can't know for sure that, for example, in 100 blocks, this particular validator will be the one. No, it is impossible, but you can definitely know who is going to be the next validator to validate the next block. And it is made like that so the validators can actually prepare, so they have time to decide which transactions to include into the block or not include. Then point number 2, validator assembles the block as he wishes to maximize profit. Yes, Ethereum doesn't have any constraints on what to be included into the block or what to not. It is fully decided by the validator how he wants and whatever he wants. There is a abbreviation in the braces. It is called maximal extractable value, which actually means that on top of proof of stake consensus thing, there is an add-on that validators can use, like a special software that validators can use together with the vanilla Ethereum consensus. So this software knows which transactions to pick and in which order to apply them. So this validator receives the maximum possible profit. This profit is not in the fees. It is actually because there is a decentralized finance activity on Ethereum. So there are some tokens and several transactions can trade those tokens, and you can find ways of how to extract something from those transactions if you execute them in a particular order. And this software basically allows validators to handle those cases. Then point number 3, validator executes block transactions one by one and send the block to peers. Yeah, so the key point here is that the order of transactions in a block is super important, and they are executed from the top to the bottom. Point number 4, at the end of each epoch, attestation on block validity begins. Yeah, so this point is connected with the proof of stake consensus. What is an epoch? Epoch is a set of 32 blocks, after which there is a special period called attestation period, when every validator, every 400,000 of them, or even more, provide attestation whether they believe the block is valid and everything is fine with this block or not. If validators think that the block is valid and everything is okay, the epoch where this block is stored gets called as safe. This means that it is unlikely for this block to be reorganized. And point number 6, when another epoch gets added on top, so when the epoch on top is safe, then our epoch, that is one behind, gets called as finalized. So at that point, when you can definitely be sure, like 100%, that this finalized block can never be reorganized. Why? Because proof of stake consensus doesn't allow that in the first place. And if you're a hacker or a malicious user, you have to have gained control to at least 1/3 of the validators, which is billions and billions of dollars, to create this kind of attack, which is like literally impossible. Okay, so if you have any questions, please ask. Maybe I can open, for example, this diagram.
Okay, thank you for a lot of time. Thank you for a lot of all the students, all the participants, and maybe we have a question. What next big update?
What next big update? Yeah, so right now Ethereum prepares a Shanghai update. They will allow validators to withdraw Ethereum from the consensus. So right now you can only become the validator, but there is no way to unbecome the validator. And it is a feature they didn't want to include in the merge when Ethereum switched from proof of work to proof of stake, because the merge was already a huge update and a lot of things have gone wrong. So they decided to postpone this fork pretty much to probably somewhere in March. Yeah. And once they apply this fork, consensus will slightly change. For example, we have here voluntary exits and also information about the validators. So right now, those fields are empty, and after the fork, they will have something.
Thank you. Maybe we can finish. Wait for materials and see you soon. Let's talk about smart contract. Yes, smart contracts on the next lecture. And about, I'm sorry, we have a question. You can use microphone if you want.
What is state? Is it calculated below all nodes separately from the transactions with the shares away? Yes, of course. So state is the global like truth about Ethereum, and this truth has to be maintained by every node. And this truth obeys the rules of the proof of stake consensus. And that is how Ethereum actually works. And that is why its users are sure that for example, if they send a transaction to a node that is located in the United States, they will have the same outcome if they send the transaction, for example, to the node that is located in China. And this state is global. It is shared by every node, and this state can only be updated by the transactions that are placed in the block when the block gets accepted.
Okay, I will try to ask this voice. Can you hear me?
Yeah.
Okay, so blockchain is basically a database where all blocks link together in some way by using the hash. Each block is connected to others. But the state, I not quite understand the concept. So how it can be represented? So is it also like a database where some account is some values?
So how Ethereum represents the state low level? So imagine so basically access addresses that have something in them. So empty addresses are not tracked at all, but the addresses that, for example, have Ethereum on their account or ever sent a transaction, so their nonce is not zero, or they are smart contracts that saved something into them. All of this is represented in a Patricia Merkle tree, where every leaf of the tree is actually the bits of the state. What I mean by the bits of the state, the smart contract has special slots where it can store variables.
So maybe Artem lost connection, and we can finish today, I think. And if you have some question, please try ask Artem in the classroom. Please, I'm sorry, but we have some problem with connection. Thank you for a lot. Yes, I'm sorry. Okay, and see you soon. And I will add information about our new course, Solidity Smart Contracts, and you can do registration and joining. Okay. Goodbye. Goodbye.
Bye-bye. Thanks.
Bye.